All right, number 7 says to determine whether the graph represents a function, I'm going to be using the vertical line test, which tells me I'm going to try to draw some vertical lines through these dots. Oh, as vertical as possible, sorry. On this screen, it makes it a little hard. So each time I draw a vertical line, for each of these vertical lines, each one of those only passes through the dots one time. So I'm going to say, yes, it is a function, and I can simply say it passes the vertical line test. Not just the line test, it needs to be the vertical line test. Right, number 8, again, I'm going to do the vertical line test. So I'm just going to draw several vertical lines, and each of these, this one passes through my graph once. That is totally okay. So that, again, yes, this is a function, and I'm going to say the graph passes the vertical line test. All right, number 9, again, I'm going to apply that vertical line test. So I'm just going to start drawing some vertical lines. I've already got issues because this vertical line passes through twice. A vertical line is only allowed to pass through one time, so this is no. And I'm going to say the graph does not pass the vertical line test. Okay, number 10, write a real-life problem to fit the data shown in the graph. Is the domain of the function discrete or continuous? I'm going to answer the second part first. Is it discrete or continuous? I'm going to say continuous. This is a connected graph, so all whole numbers and fractions and decimals would be included. And then a real-life problem, I just need to think of something as one thing goes up, the other thing goes up. I'm going to think of when we did the graphing stories. I'm going to say the time in seconds, and I could say, I guess, I'm going to say person walking up the stairs. Person walking upstairs, and I'm just going to say the height from the bottom step. So if I did this, the height, as time goes on, their height from the bottom step is going to gradually, at a steady pace, go up, because I'm assuming they're walking at a steady pace up those stairs. So hopefully that is a good example for me. I should not see the same example for you. You're going to think of something different. Right, number 11, evaluate the function when x equals -2, 0, and 1. We are going to have 3 different answers. We're going to have an answer for g of 0, -2, whoops, sorry. We're going to have an answer for g of 0, and we're going to have an answer for g of 1. Okay, for -2, we're going to put -2 in for our x. We're going to get 6 times -2. That will be -12. Then I'll plug 0 in for x, so 6 times 0 is 0. And then we'll plug in 1 for x. I'll get 6 times 1 is 6. Number 12, once again, evaluate the function when x equals -2, 0, and 1. We're going to have 3 answers, h of -2, h of 0, and h, whoops, not f this time, h of 1. Okay, for the first one, we're going to plug -2 in for the x. So I'm going to fit 1.5 times -2 plus 9. 1.5 times -2 is -3. -3 plus 9 is 6. Next time I'm going to plug in 0, so 1.5 times 0 plus 9. 1.5 times 0 is 0. 0 plus 9 is 9. And then plug in 1. 1.5 times 1 plus 9. 1.5 times 1 is 1.5. Plus 9 is 10.5. Okay, number 13. It's more evaluating. Evaluate the function when x equals -2, 0, and 1. Again, I'm going to set my problems up. So I'll have f of -2, f of 0, and f of 1. The first time I'm going to plug in -2 for the x, I'm going to have 1 minus 3 times -2 minus 2. If I can type this in my calculator in one step, which would be the best thing to do, but I'm going to otherwise follow the order of operations. I'm going to do this first. -3 times -2 is 6, so I'm going to have 1 plus 6 minus 2. 1 plus 6 is 7, minus 2 is 5. Next, I'm going to plug in 0 for my x. 3 times 0 is 0, so 1 minus 0 is 1. 1 minus 2 is -1. Now I'm going to plug in 1. 3 times 1 is 3, so I'm going to have 1 minus 3 minus 2. So 1 minus 3 is -2. -2 minus 2 is -4. Okay, a student student commutes from home to school by walking and then riding a bus. Draw a time versus speed graph to represent the situation. So I'm going to have time, probably in seconds, and then I'm going to have speed. All right, so we need to think anytime, we want to think as much as we can what's happening to the situation, and the speed is going to be whenever the person stops, we have to go back down to the bottom. So I'm going to say the student is probably walking at a constant speed, and then they probably get to the bus stop, which means they're going to come to a stop. I'm going to have the speed stay down here for a little bit because I'm guessing they're not running late. They're going to have to wait for the bus, and then I'm going to go up a little bit, and then this time I'm going to go back to a constant speed, but please notice that this speed is faster than this speed because they are now on the bus going to school.